Hello everyone, this is Engineer Selassie from Yellow Academy and Brain Boosters, and today we are going to discuss about Chapter 8, the multi-level feedback queue. As assumed that last chapter we discussed about a lot of scheduling, first come, first serve, short job first, round robin and the like. But all this kind of scheduling, they are assuming they know the burst time of the process. Okay, how much time the process will take in the CPU, but that is not real. That is very difficult to know. If you open the Word or other application and you just know how much time it will take in the CPU, that is unrealistic. So this is the situation. So let's see the new level of scheduling, the multi-level feedback scheduler. So let's get into it. So as the name is multi-level feedback queue, MLFQ. First described in compatible time sharing system, CTSS, by Corbato, and a scheduler that learns from the past to predict the future. What this scheduler does, it will predict the behavior of the process from its history from the past, whether it is interactive or CPU bound process. It will know from the history, because as I have discussed the problem of other scheduling mechanisms, they assume like the burst time of the process is this much, that much, but that is not possible. So the objective of the MLFQ, optimize turnaround time and run shorter job first. Okay, shorter job first, and again minimize response time without a prior knowledge of process runtime lengths, as we have seen now. So these are the 2 points: turnaround time and response time. A scheduling policy that learns from the past to predict the future. So it is really interesting. I hope you will be interested as well. So let's see, because round robin was good for the response time, but it is very bad for turnaround time. And shortest job first, it was good for the response time, but for the turnaround time it was bad. That's why we add another scheduling others. Okay, so MLFQ basic rules. MLFQ has a number of distinct queues. Okay, a number of distinct queues. Each queue is assigned a different priority level. A process that is ready to run is on a single queue. Then a process on a higher priority queue is chosen to run on the CPU. So it has a lot of queue, and the priority, as per the priority, it will be given. So use round robin scheduling among processes in the same queue, because they have the same priority. If two processes are in the same queue, then we will use round robin. So this will bring us to the first two rules of MLFQ. Rule 1 says if priority A is greater than priority B, A runs, B doesn't. Then rule 2, if priority A is equal to priority B, then A and B runs in round robin fashion with time quantum. So this is the first two rules we have about MLFQ. So the basic rules, how is MLFQ set the priority level of the queue now? Okay, so MLFQ varies the priority of a process is based on its observed behavior rather than fixed values. It uses history of each process. What does it mean? Example: a job repeatedly relinquished the CPU while waiting IO operations keep its priority high because it is interactive process. A job uses the CPU intensively for long period of time. This is reduce its priority because it is CPU bound process. So in MLFQ, the interactivity and the CPU boundness will determine the priority level. So if it is interactive, it has higher priority. If it is CPU intensive, then it will reduce the priority. So as you can see, MLFQ example, if we have 1, 2, 3, 4 processes, as you can see, as long as A and B are in the higher priority queues, they will be scheduled first. Then once A and B are in the same queue, then round robin will be applied on them. After they finish, then C will finish. After C, process D will be finished because process D is low priority. Low priority means CPU bound. It will need a lot of time to complete its process, but high priority means it is interactive, like gaming. Maybe they need a keyboard to like gaming applications. So for interactive processes, MLFQ give high priority. How to change priority? So MLFQ priority adjustment algorithm. Now this will take us into another rules. Rule 3, when a job enters the system, it is placed at a higher priority because at this moment we don't have any information. So any process comes, it will be placed in the higher priority. Rule 4a says if a job uses up an entire time slice while running, its priority is reduced because it moves down on the queue because it is CPU bound, because it doesn't finish. It takes all the time slice. Rule 4b says if a job gives up the CPU before the time slice is up, it stays at the same priority level. So in this manner, MLFQ approximate short job first scheduling. So as you can see, rule 4a and rule 4b. Rule 4a, it says if the system, if the process takes up all its entire time slice, then it will move down in the queue. But if the process gives up the CPU before the time slice, then it will stay in the same priority level. It will not go down. So as an example here, a 3 queue scheduler with time slice of 10 millisecond. Okay, so as you can see here, long running job over time. So rule 3 applies here because queue the process is here, so it is in its priority. Again, rule 4a and rule 4b. If it takes too much time, like for example with time slice of 10 millisecond, but as you can see in the down, most probably this one is process A, or any process which takes up all will be down in the queue, and the process which gives up the CPU before the allocated time will be in its priority level. So example 2, along came a short job. For example, while a process is going, for example, at the first, the scheduler doesn't know the runtime of the new process, assuming it is short. If it is, then it will finish early. Just approximate short job first. What does it mean? As you can see, A, we have job A, a long running CPU intensive job. But if you see job B, a short running intensive job, 20 millisecond runtime. So what happens is A has been running for some time, and then B arrives at time t is equal to 100, for example, here. So as you can see, the process A is already in the lower queue because it is CPU intensive process. But once at 100 seconds, when process B comes, rule 3, as per rule 3, it will go directly into the higher queue because we have 3 cubes here. Then what happens after 20 microsecond, because it has 20 microsecond, but after 10 microsecond this process doesn't finish. So what does happen? The system will take it to the lower queue, because as per rule 4a, if the process doesn't finish in the time slice, then it will go, the priority will go down to the next lower queue. So that's why B go down here and it's completed. After that, in the same lower queue, process A or job A can continue. Example 3, what about I/O assumption? For example, job A long-running CPU intensive job. We have a long-running CPU intensive job, and job B is an interactive job that needs the CPU only for 1 millisecond before performing an I/O operation. So the main idea here is a mixed I/O intensive and CPU intensive workload. So the main idea is the process will not be penalized by reducing its priority if it gives up CPU before time slice completes. The MLFQ approach keeps an interactive job at the highest priority, because as you can see here, B needs the CPU only for 1 microsecond, but the time slice is 10 microseconds. So because after 1 second, it will go for I/O operation. So as you can see, then it will come. So after 1 second again, so as per rule 4b, our job B will not go down to the next queue, okay? But as you can see here, job A long running process, so it will go down. There is no doubt. It will go down, and if you see here, the first, the CPU will be allocated for process B because it is interactive. After that, the CPU will be idle. In that idle time, A can run. Okay. Then when B comes again, B will take up, as you can see, for 1 microsecond. Then after 1 microsecond, A will go, but the priority level of A is down because it is CPU intensive and it will continue like that. I hope you got the idea. Now, what is the problem with the basic MLFQ? The first one is a starvation problem. What does it mean? If there are too many interactive jobs in the system, long-running jobs will never receive any CPU time. This is for sure, because the priority level is high. 2, a process may change its behavior over time. For example, now a process which is CPU intensive and it is in the lower queue, maybe it will change its time into I/O intensive. So how the system MLFQ will respond to this? So a process may change its behavior over time. CPU bound process become IO bound process. However, MLFQ does not recognize that. CPU bound process and IO bound process. The third one will be game the scheduler. For example, after running 99% of the time slice, issue an IO operation, because as per our rules, if a process doesn't occupy or doesn't pass the time slice, then it will not go to the lower queue. So if some kind of gamers, if after running 99% of the time slice, issue an IO operation, it does not consume entire time slice, remain in the current queue. So if this kind of game happens, how the MLF queue response, and the job gain a higher percentage of CPU time by playing like this, gaming, the MLF queue system. So how we are going to address these three problems? Then what happens is the priority boost. The priority boost is one of the solutions for the priority boost means solve starvation and a CPU bound process becoming interactive by introducing rule 5 below. What does it mean? Rule 5, after some time period S, okay, they call it voodoo magic because no one knows this time, but after some time period S, move all the jobs in the system to the topmost queue. And what is a good value of S will be very difficult, but any process which is in the lower queue, they will get a chance to come to the upper queue after some time of S, this S, some period of S, but nobody knows what time it will be. For example, a long-running job A, okay, as you can see here, with two short-running interactive job B and C, as you can see B and C. So this one in the left, what you see here, we don't have any priority boost. So if we don't have any priority boost, as you can see, the CPU will be taken by the two interactive processes B and C, because A will not get any chance to be executed because there is no priority boost applied here. But if you apply priority boost, for example, for every 50 microsecond or second, then what happens is after A and B with round robin fashion, they run in the CPU, at the end of 50 seconds, then the queues, the process in the lower queue will get a chance, you see, for 50 seconds. Then after 50 seconds, then the interactives will take over. Then after that, the lower will get. So in this kind of function, this priority boost really helpful to give a chance for the CPU bound processes. So this is the idea. By doing so, the starvation problem will be solved and the CPU bound process will become interactive as usual, okay, as you can see. So this is the first solution. And better accounting, this is also very important. Better accounting means how to prevent gaming of our schedule. That means if the process try to game, okay, the system by after it takes 99% of its time slice, then it will give IO operation, then again after it will gain, so it will gain the CPU for a long time. To avoid this, what we are going to do, rule 4, rewrite rules 4A and 4B. What we are going to, once a job uses up its time allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced. It moves down on the queue. So this is the revised version of the rule, because it will not allow gaming, because that's what it does. So whatever it is, the process should go to the lower queue. So as you can see, without, and this is gaming tolerance is in the right direction, and in the right side and the left side without any gaming tolerance. So without any gaming tolerance, as you can see, process B, it will run, then at the 99% it will give IO operation, then again it will be in the same queue and it will continue running. again in the same queue. So only 1% will give for the other processes, as you can see. So it will manipulate the system like that. But what it does is, if there is gaming tolerance, as you can see, whatever it is, the process which is running in the higher, once it finishes time allocation, then it will go down to the lower queue. Again, after some time, it will go down the lower queue. So in this way, we can allocate the game. So turning MLF queue and other issues. That means, how do we prioritize the MLF queue scheduler? How we are going to prioritize? That means, for example, number of cubes, how many number of cubes, time slices, okay, per queues, best value for S. So all these questions need to be answered. So most of the time, the high priority queue will be given short time slice because they are interactive for sure. Example, 10 or fewer milliseconds will be allotted for higher priorities. For low priority queues, long time slice will be, because it is CPU bound for sure. So 100 millisecond or something will be assigned. Example, 10 millisecond for the higher, here 10 millisecond, and 20 millisecond for middle, and 40 millisecond for low. So low priority, longer time, it will need longer. So in that way, longer time slice will be given. So this will give you an idea. So to see some example, practical example, the Solaris MLFQ implementations. For Solaris, the time sharing scheduling class TS use a set of tables, and it has 60 queues and a slowly increasing time slice length. That means the highest priority, it has 20 millisecond, and the lowest priority, a few hundred milliseconds will be given, and priorities boosted around every 1 second or so. So priority boost is very important. So they will give every 1 second. So all the processes in the higher queue or in the lower queue will get a chance. For FreeBSD, a mathematical formula is used to determine priorities using decade over time. And for other operating systems, higher priority levels are given to the operating system kernel services and allows users to give an advice to help set the priority level. Example, the nice command. This is nice command in the small letter, okay? So just in summary, MLFQ summary, the refined set of MLFQ rules. Rule number 1, if priority A greater than priority B, A runs, B does not run. Rule number 2, if priority A is equal to priority B and B run in the round robin fashion. And rule 3, when a job enters the system, it is placed at the highest priority. And rule number 4, once a job uses up its time allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced. It moves down in the queue. Rule number 5, after some time period, S, move all the jobs in the system to the topmost queue from lower priority to higher priority. In this way, we can assure fairness and all the processes will get a chance. I hope this was helpful. In general, this is all about the MLFQ scheduling system. and I advise you to read the book in addition to this. So that was it for this chapter. This is I am Engineer Selassie from Yellow Academy in Brain Boosters, and next time I will come with chapter 9 of the book. And thank you so much. Bye bye.